morning for you chemistry students. Welcome to your last lesson on acids and bases and equilibrium. And it is a doozy. We are going to be pulling together stuff from the last 3 lessons. So 3 lessons ago we learned about kind of weak acids and weak bases and the Ka and Kb values. Then we did salts and figuring out if a salt was going to be basic or acidic. And then we looked at titrations and reviewed the fact that if you have a strong acid, strong base titration, like what we would have done in 3U chemistry, that at the equivalence point, when all of the hydrogens have reacted with all the hydroxides, we should end up with a neutral pH or a pH of 7. But today we are looking at a weak acid being titrated with a strong base, and we could have also done a weak base being titrated with a strong acid, but we'll just do the one example. So in those types of titrations at equivalence, we're not at 7. And from our last lesson on Thursday, you might recall that you are expecting a pH at the equivalence point to be greater than 7. So when it's a weak acid with a strong base, when it is at equivalence, it should be basic. Okay, so it's a fairly lengthy question with 2 parts. Part A is going to review the stuff we did 3 lessons ago, and then part B is new. All right, so we have 20 mils of a 0.3 mole per liter methanoic acid, that's a weak acid because it's a carboxylic acid, being titrated with 0.3 mole per liter sodium hydroxide, which is a strong base. So part A wants to know the pH before the titration. And before the titration, all you do is you have acid in a beaker. So we're really not doing anything with the titration. We're figuring out the pH of that acid. So because it's an acid, we are expecting it to be below 7. That's our prediction, so you can make sure you have accurate answers. And then from our last lesson, with this type of titration, we're expecting something to be above 7. Not 7 because it's not strong acid, strong base. Okay, so that's just our predictions. Okay, so part A, which as I said, this is review. So this is before the titration, which really just means we have a beaker or a flask of acid. So only a weak acid. And we want to know the pH is what we're looking for. Okay, so our acid, we're going to set up a rice table. So we've got methanoic acid, and of course we kind of assume that what's happening with a weak acid is that it is reacting with water molecules. Okay, so I might just put in here aqueous, liquid. And because it's an acid, it gives hydrogen to the water molecules. It makes hydronium ion. And then what we're left with is this ion here, COOH with a -1 charge. Okay. So as soon as you see the hydronium, you know you're talking about Ka values, and it's going to be acidic for sure. So in our rice table, we need to start off with our initial concentrations. So the acid we were told is 0.3 moles per liter. The water we'll just ignore because it's liquid, so it doesn't have a concentration. And then, of course, at first we have no ions. Okay, so the change that happens as this reaches equilibrium is we're going to lose acid molecules, but we're going to gain ions. as it ionizes with the water. So at equilibrium, we have 0.3 minus x, x, and x. So this is at equilibrium, and the equilibrium constant for methanoic acid is also at equilibrium. So we can set up our equilibrium equation now, where Ka for methanoic acid is going to be equal to products, so x times x raised to the 1 and divided by 0.3 minus x, or the reactant, which is also raised to the 1. Okay, so this value you can find on page 803 of your textbook. So it is 1.8 times 10 to the negative 4. And that is going to be x squared over 0.3 minus x. Now, we could expand this by bringing this up, and we would have a number, and we'd have 1.8 times 10 to the negative 4x, and we'd have x squared. And technically, eventually we could solve it with a quadratic equation, but we can also do the thing that we learned a couple lessons ago called the 100 rule. So we're going to check to see if this is needed or not, or if it's so tiny we can ignore it. So the 100 rule says you take the initial concentration and you divide it by the Ka value. And if it's greater than 100, you can ignore that x, because the change is so tiny it's not going to make any difference. And this is definitely greater than 100. Okay, so we're going to ignore x, the minus x, of course. X squared is still significant. So that gives us 1.8 times 10 to the negative 4 is going to be x squared over 0.3. Scroll down here. So then we will multiply 0.3 by this, and we're going to get 0.54 times 10 to the negative 4 is equal to x squared, and then we will take the square root of both sides and solve for x. So x is 7.3 times 10 to the negative 3. And x is in our rice table, so it's actually in moles per liter because it is a concentration. And it is equal to our hydronium ion concentration. So we're almost done. So based on that, if we're trying to solve for pH, this goes back a few more lessons. pH is the negative log of the hydrogen ion or the hydronium ion. So negative log of 7.3 times 10 to the minus 3. And remember, I don't put the negative in my calculator usually. I just take the log of that number. So it'll come up 2.14, negative 2.14 I should say, but then you realize that you ignored that negative sign. So 2.14. And that is actually obeying our significant digits because our concentration had 2 significant digits, so our pH usually has 2 decimal places. Okay, so that is before the titration, which is a very reasonable answer because it is an acid, so it should have a pH in the acidic range. Now, and that was review. So now we are going to look at the equivalence point. So equivalence basically is saying that we have to have balanced out all of the hydrogen ions with all the hydroxide ions that we're titrating with. So that is really what's going on. So all hydrogens from the acid are reacted with hydroxides from the titrant. Okay, so that's what is happening. So let's just write that out. So here we've got our acid in our beaker that we just figured out the pH is 2.14. And then we start adding drop by drop sodium hydroxide from the burette. And this is just a double displacement reaction. So the hydrogen from the acid and the hydroxide from the base are going to make HOH, or water. And we're also going to have ions. They're really just floating around as ions. We're going to have sodium +1 ions with COOH -1 ions. We usually write them together, but we know because they're aqueous, they really are not bonded in any way. Okay. All right. So this is where we have to realize why we end up with a weird pH that isn't 7. Because the water is neutral, okay, and all of this is gone. So this is all turned into water and these ions when we have reached equivalence. Now, if you think of our last lesson, sodium is coming from a strong base like sodium hydroxide. So we can end up ignoring it because it is going to be causing it to be neutral. Water is definitely going to cause it to be neutral, but this ion here is going to then continue to react with the water and is going to cause another reaction to happen that is going to change the pH from 7 to obviously something basic. So this is the problem. All right, so in our rice table at equilibrium, this ion is going to continue to react with water. And this is going to be in equilibrium. So it is definitely not able to donate a hydrogen, but it will certainly accept one. So we'll get back our methanoic acid. And then water is going to lose the hydrogen, so we get OH. And as soon as you see OH, this is what we call a base hydrolysis. So we can have acid hydrolysis or base hydrolysis depending what is reacting with the water. So if we're making OH, it's a base hydrolysis. Okay, so this is now the rice table that we want to do to figure out what the pH is. And we're going to ignore water again. I'm going to leave this column for a second and do the easy stuff. So when we first start off, we're going to have 0, 0. We're going to gain X, we'll have X, we'll have X. So this is the tough part right here, and it can be much harder in other questions, but we're going to do a nice easy example. We have to figure out what is the concentration initially of that ion. Now, because of the nature of the question we've done, it told you at the beginning that you have a 20 ml sample, but they are matching concentrations if you notice. It was 0.3 mole per liter weak acid and it was 0.3 mole per liter strong base. So at the equivalence point, because this is a monoprotic acid and this is also just a singular hydroxide in this base, if we're going to react all the hydrogens with all the hydroxides to make water, we're going to need equal volumes for that to happen. So if you started with 20 mils of the acid, This is going to happen when you have added 20 mils of base. That's when you're going to have everything perfectly reacted to make water. So questions can be a lot harder if you are dealing with acids that say have 2 hydrogens, but the base only has 1 hydroxide. Everything changes. But in this situation, when you have equal concentrations and you have single hydrogen, single hydroxide, the concentration is simply going to be cut in half. Okay, so it's going to be half the concentration, and basically it's because you need equal volumes. So you're going to be doubling your volume, which will half the concentration. So we basically took 0.3 divided by 2, and that is the only type of question we will do this year. But they can be obviously much more complicated. So as this changes, we're going to minus x, and then we're going to have 0.15 minus x at our equilibrium. Okay, so the big difference now, when we set this up in our equilibrium law equation, because we have OH over here is what we're actually making, when we set it up, it has to be Kb because it is a base. So we're going to have x squared, x times x, all over 0.15 minus x. Okay, now we can't just look up that Kb value. So if you recall, you can calculate it. Kb is going to be found by taking the Kw, or 10 to the minus 14, and divide by the conjugate acid. So it's going to be methanoic acid, its Ka value. So we're going to have 10 to the negative 14, and we are going to divide by 1.8 times 10 to the negative 4. And that's going to give us 5.5 times 10 to the negative 11. And this is for our ion. Okay. So I should just write that here, COOH negative. All right. So now if we plug that in, 5.5 times 10 to the negative 11 equals x squared over 0.15 minus x. And again, let's check out the 100 rule, because if the 100 rule doesn't work, we are stuck with a quadratic equation. So we will do 0.15, and we're going to divide by 5.5 times 10 to the negative 11. You have to use whatever you're dealing with. Is it Kb or Ka in our previous part, but this is going to be the Kb. That is also greater than 100, which frequently is the case. So now we can expand this 0.15 times 5.5 times 10 to the negative 11, 0.83 times 10 to the negative 11 is equal to x squared, square root everything, and we have 2.9 times 10 to the negative 6. Notice how this is hydroxide ion concentration, is what x is this time. So based on that, we can figure out the POH, because it's the negative log of the hydroxide ion concentration. So negative log of 2.9 times 10 to the negative 6. Need a lot of paper for these questions. 5.54 is the POH. So if you stayed there, you weren't thinking straight because you know you're expecting a basic pH. So to get pH, you want to take 14, subtract the pOH, and that's going to give us 8.46. So that is a basic pH at equivalence. And in our last lesson, we basically looked at the fact that that is always going to be the case when you have a weak base and a strong, or sorry, a weak acid and a strong base titration. At equivalence, it will definitely be basic. Okay, so that is it. Definitely ties in everything we've basically done in acid-base equilibrium. And I'm going to give you an assignment just with a different substance, but basically you can practice doing those exact same types of calculations on the assignment.